Good afternoon, everybody. My name is Bhardwaj, and I am on the faculty of Mechanical Engineering at IIT Bombay. Today, I'm going to talk about the survival of coronavirus in a respiratory droplet which has been deposited on a surface. This work was done in collaboration with my colleague, Professor Agrawal. This talk is based on an article which we just published in Physics of Fluids. So, if you want any details about the work, you can actually refer to the article. Regarding the motivation of this work, this is probably on everybody's mind right now, how the coronavirus is transmitting through the respiratory droplets. So as we know, when there are coughing events, sneezing event, or even we are speaking, we generate droplets. These droplets carrying coronavirus can go to any other individual and infect with the virus. So these droplets could be of different size, as you can see here in this schematic. There are airborne droplets which are very tiny, less than 10 micrometers. There are large droplets which are greater than 100 micrometers. So the larger one actually gets deposited on the surface and so-called fomite, which has pathogens or virus. And when you touch them, you actually carry virus with you. You can infect yourself or infect the other surfaces. So we are trying to look these droplets and we want to figure out what is the evaporation time of these respiratory droplets. In the studies, people have shown that this cough cloud or the sneeze clouds can go as far as 7 to 8 meters. So even if you are very far away, you have a very good chance of the infection because these droplets can deposit at several places. In the previous studies, people have looked at the survival of coronavirus on different surfaces. In a notable study, which is also very recent, in April 2020, in New England Journal of Medicine, the researchers looked at the survival on different type of surfaces. So these were not really droplets. This is just the virus on different surfaces, and they want to look at the evidence of viable virus on those surfaces. So what they found that the virus survives on these surfaces up to 80 hours on these surfaces, and the lowest was copper. So they argued that because of the and microbial property of copper, the survival time is lesser. But it's hard to say that how active still able to infect these viruses are. And it is also not fully known that how much dose of viral particles are needed that can infect us. So in a way, we can actually say that the droplet in which the virus is there could be a good metric of the survival of the virus. So previous studies, in fact an old one, shows that the viral titer reduced exponentially after the droplet dried on the surface in different conditions. So they actually tested different type of viruses in a droplet and they dried it on the glass slide. So they kind of correlated the lifetime of the droplet with the virus. So in this study, we kind of assume that the virus dies when the droplet is not there, or the chances of the survival of virus is proportional to the drying time of the droplet. So in order to find the drying time, first we need the size. So we look at the distribution of sneeze droplets. In the literature, there are several studies which have reported about the sneeze droplets, the size of the sneeze droplets. So a notable one is by Dungit in 1946. After that, there are several. In a recent study by Zhao, I think we check the size. So for example, these are the distributions of the size plotted on the left part of your slide, and we can see that the sizes actually ranges from 100 to all the way to 300 micrometers. So based on this data, we actually say that these droplets are 1 to 10 nanoliters, and their probability distribution function of the size is plotted right here on the right of the slide. And the average diameter is around like 190 micrometers, and this is close to around 4 to 5 nanoliter droplet. So with a given size, we can actually now look for the evaporation time of these droplets, and we can figure out what is the drying time and connect that to the survival of the virus. So we pose our research question as follows. So we want to find the drying time of large respiratory droplets, which can actually go on a surface and deposit, and we can touch them and infect. And we want to do that in several conditions and surfaces. We want to find the relation of the drying time as a function of temperature and relative humidity, and the contact angle. So contact angle is basically the type of surface on which you are putting these droplets. And once we have the drying time, we want to find out is there any connection between this drying time and the growth rate of COVID-19. So in this study, we have said that the temperature is from 25 to 40, which actually represent an ambient conditions, ambient temperature conditions, outer weather conditions, and humidity from 10 to 90%. So the contact angle has been taken for several surfaces, for example, glass, which is hydrophilic, wood, which is slightly larger contact angle than the stainless steel, around 30, and the touch screen of smartphone, where you have a larger contact angle. Before we go to this tiny respiratory droplet, much is known about these bigger droplets. So we can actually understand from these bigger droplets while we model the drying time of these smaller droplets. So for these microliter droplets, which actually comes on a surface, the spreading time is on the order of micro to milliseconds, and the evaporation time is on the second to minutes. So impact time actually scales as diameter to velocity. So for a 1 mm droplet, which is impacting with 1 meter per second velocity, the spreading time is on the order of 1 millisecond, which is actually much lower as compared to even the blinking of human eye. So this is an experimental image where we actually looked at the deposition of such droplets. So one thing is clear, there are two stages of these droplets while they impact on a surface. One is the impact and other is the evaporation. So impact is very fast, and while the evaporation is slower. Other thing is clear that once you deposit them, after the impact, they become spherical cap. So you can actually assume their shape as the spherical cap after this tiny time. So what we can say now that we can take a spherical cap on a surface because the impact time is so small that can be ignored with respect to the evaporation time. So here is the schematic of the problem. We take a droplet, there is a virus right here, and there is a diffusion of liquid vapor outside the droplet, which actually dry out the droplet, and there is an evaporation induced flow. The virus could be subjected to the shear stress, as you can see here. So our assumptions for this model are, we consider diffusion limited evaporation, so there is no convection outside the droplet. The contact line remains pinned throughout the evaporation. There is a quasi-steady evaporation. So what does that mean? The droplets evaporate very slowly so that the shapes remains unchanged, or we can actually assume the unsteady terms of the vapor concentration as zero. So there are very small changes in the vapor concentration outside the droplet as it evaporates. So this can be quantified by the ratio of 2 times. One is the heat equilibration time to the drying time, which is, this relation is actually given by Larson in 2013 paper. So this value comes out to be around 0.05, which is very small, even at the extreme conditions we have considered. So our droplet actually is in quasi-steady evaporation. These are the formula which connects the volume of the droplet to its wetted radius and the height, and this is the contact angle. Now we first estimate the shear stress. So shear stress can be estimated by just considering first the flux, which is outside the droplet. And this flux can be correlated to the evaporation induced velocity in the droplet. And this evaporation induced velocity coupled with the profile, linear velocity profile on the droplet as has been seen here, can be, the shear stress can be estimated. The shear stress is a function of eventually the evaporation flux, the diameter of the virus, and the density of the fluid. So the diameter of virus can be taken as 125 nanometer, which is kind of established with the previous measurements, and we took around 1 to 10 nanoliter droplets, and what we found there is the maximum shear stress is actually very small. It's on the order of 0.01 pascals. So here we can say that shear stress is not very high to remove the virus or to kill the virus. So the way it can be removed is the droplet dries out and then the virus dies. So this is the result. We are plotting, in x-axis is the volume of the droplet and y-axis the drying time. So as you can see here, first the red plots, the red curve shows that we are varying the temperature, and there is a significant change while the temperature varies from 25 to 40. The 40, the time is very small as expected. If the ambient temperature is higher, the droplet will evaporate faster. The result for the contact angle shows that as the droplets become droplet is at larger contact angle, it evaporates slowly. For a hydrophobic surface, the evaporation slows down. And the largest change we saw in humidity. So we can see here a larger humidity means very large evaporation time. So we found three parameters that which are humidity, temperature, and contact angle, which actually influences our drying time. Then we plotted the mean and standard deviations of the PDF of drying time, because we have drying time for a range of the volume that is from 1 to 10 nanoliter droplets, and these are the plots. So this error bar actually showing the distribution of the time, and this is actually this bar is actually for the conditions we have considered. So for example, this is the baseline case, and this is the case where we are hitting the ambient temperature or increasing the ambient temperature. This is the case of hydrophilic surface, and this is the case of hydrophobic surface. And this is for the higher humidity. As we said that the larger humidity, the time is very large and the survival increases. So what we understood from this plot is the survival of the virus increases roughly by 5 times in a humid conditions, and it actually decreases by 2 times in a hot weather, and it is increased by 1.5 on a hydrophobic surface. So there are something we understand from this parametric study. And then what we did, we actually plotted the growth rate in different cities. So we want to ask a question whether this drying time is kind of connected with the growth rate of the pandemic in different cities. So this is the data of different cities. We selected 3 cities: New York, Chicago, Los Angeles, Miami, Sydney, and Singapore. We did not consider any Indian city because when we did this study, there was no Indian data. So we are actually working currently to include more cities. So we have considered that when the infections become 100 or more, we start to plot the data, and then we fit a linear curve using least squares fitting to find the growth rate. So these lines actually shows different fitted curve to different infections in different cities, and the slope of these lines actually the growth rate, which is the change in the infection per unit time, or where time is day here. We also can record the ambient conditions, which is ambient temperature and relative humidity in different cities. And you can see there is a range here. This range accounts for the change in the day and the duration of the pandemic. And now we can actually consider the droplets in these cities, because we have the ambient conditions here. And then we can actually plot the growth rate and the drying time together. So this is the plot where we have the growth rate of different cities. As you can see, this bar, the New York City, has the largest growth rate. The Chicago is slightly lower, Los Angeles even smaller, and then Miami, Sydney, Singapore is the lowest. Right? And based on the ambient condition data, which I showed in this slide, we calculate the drying time. So we take the mean of this range and calculate the drying time. So this error bar actually represents the fluctuations of the outdoor weather. So these drying times are actually plotted here for these respective cities. So what we see here, the drying time actually is much larger for the New York and Chicago as compared to the cities which are having low growth rate. So there appears to be a weak correlation between the two. So where the cities where the growth rate is larger, the drying time is larger, which really means that the droplet survives more, and there are more chances of infecting someone with that droplet, or the virus survival is longer in these cities, and that's why the growth rate is larger. So conclusions, we have examined the likelihood of the survival of the virus, coronavirus, in the respiratory droplets. We have considered a droplet range from 1 to 10 nanoliters. We have considered 3 important parameters, which are ambient conditions, ambient temperature, humidity. We have considered droplets on hydrophilic and hydrophobic surfaces. A simple model has been used, which is a diffusion limited quasi-steady evaporation model. And then we run this model for these different conditions, and we found that the likelihood of survival of the virus is more in humid environments as compared to dry conditions, or a lower ambient temperature as compared to high ambient temperature, and on hydrophobic surface as compared to hydrophilic surface. Then what we did, we calculated drying time in different cities, and then we plotted the growth rate of the pandemic in different cities. And then we found there is a weak correlation between the two. I thank you for your attention.